Well, this is the third installment of the graphing of the function f of x equals 8x over x squared plus 4. One thing I wanted to point out, I just noticed as I was waiting for the last video to process, that notice I had said here that f of 2 square root of 3 is equal to the square root of 3, but then over here I wrote minus the square root of 3. Those actually got flip-flopped, so let's fix that real fast. F of minus 2 square root of 3 should be minus the square root of 3. These are our points of inflection. Remember our local max value is 2, so the point 2, 2 lies on the graph. The local min value is negative 2. It occurred at an x-coordinate of negative 2, so the point negative 2 lies on the graph. I think I'm going to go ahead and just put those points on the graph. We've got negative 2, and 2, 2. And the three inflection points, let's see, what were those again? Those were minus 2 square root of 3, which is about minus 3.5. And the y-coordinate is minus square root of 3, which is about minus 1.7. So I'm going to put that about right here. That's one inflection point. 0, 0 is another inflection point. And the third inflection point is 2 square root of 3, which is about 3.5. And the y-coordinate is square root of 3, which is about 1.7. So these are points of inflection. This is a local max. This is a local min. And let me down here. I'm just going to write some information regarding the behavior of the function. What we found is that on the interval from where was it? Minus infinity to minus 2, the function is decreasing. And then from minus infinity to minus 2, it's decreasing. From minus 2 to 2, it's increasing. And from 2 to infinity, it's decreasing again. And on the interval from minus infinity to minus 2 square root of 3, the graph is concave down. From minus 2 square root of 3 to 0, it's concave up. From 0 to 2 square root of 3, it's concave down again. And then from 2 square root of 3 to infinity, it's concave up. And also remember that the line, the x-axis, line y equals 0, is a horizontal asymptote. So I need to connect these points together. I need to make sure that that the graph approaches its asymptote. And I need to connect the points in such a way that the graph has the right concavity and it's increasing and decreasing where it's supposed to be. So from minus infinity to minus 2 square root of 3, the graph is concave down and decreasing. And I want to make it approach the x-axis. Remember, that's the horizontal asymptote. Okay, so it's decreasing concave down. And it becomes concave up at minus 2 square root of 3, but it's still decreasing. So decreasing. Then from minus 2 to 0, it's concave up and increasing. From 0 to 2, it's concave down and increasing. From 2 to 2 square root of 3, it's concave down and decreasing. Make it concave down and decreasing. Good. And from 2 squared root of 3 to infinity, it's concave up and decreasing. And I want the graph to approach its horizontal asymptote, which is the x-axis. So this is what the graph looks like. Here are my inflection points. This point here, this point here, this point here. So the concavity changes. My local min, my local max. Notice that this is actually an absolute min, and this is an absolute max. We can actually go one step further and say not only are these local extrema, but they're absolute extrema. And that pretty much wraps it up. Again, a long example. It was necessary to do one of these, I think, because I need you to see how all of these things are used together to analytically produce the graph of a function which is somewhat complex.